You're listening to Spellbound. Welcome to episode 11 of Spellbound. I'm Julian Smith, and today's episode is brought to you by the lovely folks over at Casper, the sleep brand who's continually revolutionizing its products to create an exceptionally comfortable sleep experience one night at a time. And they're giving our listeners $50 off select mattresses. You can redeem this offer by visiting casper.com/spellbound using the promo code Spellbound at checkout. Today, we are diving headfirst into a topic which has fascinated me for a long time and I know next to nothing about. That is dark matter and dark energy. What is this stuff? Can we know anything about it for real? Is it just a theory or is it actually there? What can we know about this stuff and how does it affect us? Because we're hearing an awful lot about dark matter and dark energy these days, and it's at the forefront of a lot of conversation. So I thought it would make a great subject of conversation for today's episode. And our guest today is Mr. Richard Panek, who is the recipient of a Guggenheim Award, which is a huge honor, and he's written a number of books which are all great. This man just might know too much for his own good. He's highly knowledgeable in a number of topics, and I've chosen him as our guest today because of the book he wrote on dark matter and dark energy, titled The 4% Universe, which is one of the best-selling books on the topic. Without further ado, here is my conversation with Mr. Richard Panek. Richard, I'm excited to be talking to you. I'm a fan of your work.
Thank you.
I discovered you through your book, The 4% Universe, and you've written a number of books, The 4% Universe, The Invisible Century, a bunch of other great books, and you also were the co-author of The Autistic Brain with Temple Grandin, who was on the show a couple weeks ago.
Oh, great.
And you're the proud recipient of a Guggenheim Fellowship Award, which is a huge accomplishment. So you're just an all-around pretty impressive guy, and I'm excited to be talking to you.
Well, tell my wife that.
You should tell my wife, and I should tell your wife. How about that? Right. It's the classic hurdle. But yeah, I love the approach that you take to your studies, and I love your bio on your website, how it says that your job description is to discover topics that you know next to nothing about and just immerse yourself in them and try to expose as much as you can to other people to start conversations and, just transform people's worlds. And that's kind of the goal of this podcast. So I'm just excited to be talking to you.
Great. Well, thank you. I'm thrilled to be here.
And specifically with the 4% universe, it's interesting because there is so little that any of us know about the universe, and there's all this information coming out about, what the universe is made of, and is it a simulation? Is it not a simulation? All these like crazy ideas floating around, but the reality is we know very little about what there is to actually be known, and that's what this whole book is about, right?
Right. Yeah. I mean, that what we've always thought of as the universe, which is you, me, the ground, Earth, the sun, stars, planets, all of that, galaxies, is only about 4% or 5%, somewhere in there. Although my book calls it 4% universe. That only about 4% is in the form that we've always thought the universe was in. And the rest is in a form of matter and energy that we don't know what they are, dark matter and dark energy. And they remain mysteries.
And dark matter and dark energy make up, it's how much of the universe does it make up? It's like a huge majority of it, right?
Well, it's everything but the 4%. So it's 96%. Good
Lord. That's crazy. And we don't know much about what dark matter or dark energy is, right? It's just kind of there, and we've yet to figure it out.
Right. Well, dark matter, theorists came up with ideas back in the late 70s, early 80s, that if it's a particle, it would be a particle that doesn't interact with electromagnetism. Hence, it's invisible to us. We can't see it. And they came up with a bunch of candidate particles, and everybody would say, well, within the next 5 years, we'll have the detectors that can do it, that can find this particle because we know where to look. We know what its theoretical properties will be. And this went on, and 5 years later, everybody said, no, definitely within the next 5 years. And this went on, starting, as I said, around 1980, and it's still going on today. And I don't know if people are still saying, just give us 5 more years. But when I was writing the book, which was now about 8, 9, 10 years ago, people were still saying, another 5 years, we'll get it. And I think that they were hoping that they would find it in Large Hadron Collider, but they didn't do that. So they're running out of places to look for it in the detectors. So that's a concern. And dark energy, which is even a greater component of the universe, is the hypothetical force, if you will, that's speeding up the expansion of the universe. People assumed that the expansion of the universe would be slowing down because here's this entity with all of this matter in it. And the matter, of course, is attracting all the other matter through gravity. And so the question was, okay, the universe is expanding, but is it going to just kind of peter out at some point? Or is it going to contract and, have a kind of reverse Big Bang? And what they found, what two competing teams of astrophysicists and physicists in the 1990s found, was that the universe is not slowing down. The expansion is not slowing down, but it's speeding up. And that it's complicated to go into, but it's in the formula. It's in Einstein's equations, the possibility. And so people went, well, this thing is real. Whatever this is, this anti-gravitational force is real on the cosmic scale. And the leaders of the two teams won the Nobel Prize in Physics back in, I think it was 2011, for that discovery.
Yeah, and
that doesn't mean that we know what it is. It's just
right.
It's still this mystery.
And this is something that people, a lot of people argue about, because it determines what we're heading towards and what the universe is heading towards. Because I could be wrong about this. This is a question. Some of my questions sound like statements, but they're they're actually questions. From my understanding, there's the possibility that the universe is expanding more rapidly each day, and then there's the other possibility that it's slowing down, and then there's another possibility that's like variable, and each of these have their own consequences in terms of eternity and what the universe is heading towards, right?
Right. Well, that's right. Yeah, that's the idea that behind dark energy is that it is in fact speeding up.
Okay, and so they've actually proven now that the universe's expansion is speeding up because of dark energy.
Prove is a pretty weighted word. Okay. That's all indications are that that's the case. But you have to.
It's all still theoretical.
Yeah. I mean, they have the data and they have the theory, but they still don't know what dark energy is. That's just a term that they're using. So you can't say that it's been proven. I mean, I think that people are pretty much on board with the idea that the universe is accelerating, but if somebody comes along and says, well, this is what the teams didn't take into account, and if you look at it from this angle, the universe isn't accelerating, then you would have to look at that evidence.
How do we even know it's there if we can't perceive it?
Well, through the observations. I mean, the way that they found it was through the observations of supernovae, which are exploding stars at great distances across the universe. And if the light from the supernovae is brighter than you would expect at that distance, then it's actually closer than you would expect at that distance, which means that the universe's expansion is slowing down. But instead, what they were finding is that it was that they were dimmer.
Interesting.
At the distance that they should be. And if you see the graph, I mean, it's like, all the supernovae line up on this diagonal line, that corresponds to distance and brightness. And then at far distance, towards the right side of the graph, the straight line curves up a little bit. And that's where it's diverging from a straightforward, stable universe.
So if we don't know what it is, what is the point in differentiating between dark matter and dark energy anyway?
Well, dark matter would be a substance of some sort, which is why it's called matter. And dark energy is again, we're using the term loosely, but it would be some kind of force. It would be something that is interacting with space, that is making space expand faster than we would expect.
Okay, so the dark energy is directly related to the expansion or contraction of the universe, and then the dark matter is just a bunch of stuff. It's like almost like a black hole or something. Not that it is like a black hole, but it's like in terms of we can't perceive it the same way we can't perceive a black hole.
We can't perceive a black hole because of what it's doing with light. It's swallowing light, and that's not the case with dark matter, but it's equally imperceptible to the eye or to any part of the electromagnetic spectrum. X-rays, radio waves, and anything.
Right. Not that they're the same thing or even serve the same purpose, but that they are, for some reason, invisible to us. So what do we know about dark matter, and how do we feel its effects?
Well, it was observed indirectly in the 1960s and the 1970s. And then you could go back and say that there were observations in the 1930s that were consistent with this, but it wasn't, but the interpretation wasn't there yet. But in the 60s and the 70s, by observing galaxies, the rotation rates of galaxies, people figured out that there was something off in their velocity. If you take this swarm of gas and stars, which is what a galaxy is, if you look at a spiral galaxy like the Milky Way, it's you know what I'm talking about, right? It's that it looks like something going down the drain, right?
Yeah.
So it's this great swirl, and they're turning. They're turning, at a rate that is, fast within them, but we can't see it, but from our distance, the galaxy looks like it's standing still, but you can take measurements of it that are outside of the optical range that we use with our eyes. You can take observations of it, and you can measure the velocities of the different parts of the galaxy, how fast they're moving. And what they found was that you would expect that if something shaped like a spiral is turning, that the inner part of it would be going faster than the outer part of it. Does that make sense?
Yeah.
Okay. So the inside of the galaxy, or if you look at, if you take the analogy and say that our solar system, operates on the same principle. These things are, these planets are revolving around the sun, and Mercury is going a lot faster than Neptune, say, because it's closer to the sun, and it's spinning faster around the sun. So, in the same way, a galaxy would work in the same way, except they were finding that it was spinning at the same rate close to the center of the galaxy and at the outer edge of the galaxy. And then when they looked beyond the visible part of the galaxy, when you look at it in different areas of the electromagnetic spectrum, they were finding that there was something out there that was also spinning at the same rate, something that they couldn't see. And so, they inferred from that the presence of dark matter. You build a theoretical model and you say, well, how much dark matter would there have to be on the outside of the galaxy in order for it to be behaving in this way? And and they could do the math and run computer simulations and show that the galaxies would seem to be each of these spiral galaxies would seem to be embedded in this kind of global, much larger global something or other that they called dark matter. Now, on the scale of the universe, it turns out that dark matter has affected the way that matter gathers on large cosmic scales, so that galaxies will group together, and then they will form clusters of galaxies, and they will form superclusters of galaxies. And so the universe, I don't know if you've ever seen these models that are based on observations of actual galaxies. But the universe on a very, very large scale has a lot of strands running through it that are these superclusters of galaxies, and then a lot of gaps, a lot of big gaps between them. Mm-hmm. And they can show through theoretical models and through math that these long strands have clustered in that way due to the effects of dark matter.
Okay, so I kind of got lost a little bit a couple minutes ago, but I think I'm tracking. Let me see if this is right. So you're saying that you were talking a second ago about our galaxy is kind of spiraling as it would if it was like a bunch of water in a kitchen sink or something.
Mm-hmm, right.
And that is because of the dark matter that surrounds our galaxy?
No. What I was saying was that in a spiral galaxy, the visible part of the galaxy is spinning in a way that the outer parts of it are spinning at the same rate as the inner parts, and that violates Newton's law. So,
I see. You're saying because it should be spiraling faster on the inside than it is on the outside, but it doesn't.
Right.
And the only way to describe that is to come up with dark matter?
I wouldn't say it's the only way. I'm sure the theorists are trying to figure out some other way, but that's the predominant interpretation, and has been for the last 30, 40 years.
Okay. So we observe these facts about our universe that don't line up with what we know about how things should be behaving based on what we're seeing. And so we kind of have to say, there's something that we don't know that's going on here, and we put a label on it like dark matter or dark energy.
Right.
Okay.
Right.
So is it possible that it's not, that there isn't two separate forces, dark matter wouldn't be a force, but I mean, I wonder how they came up with dark matter and dark energy as two separate things if we don't even know what they are or what they're doing.
Well, the dark matter, that idea came up first based on those observations of galaxies that you and I have been discussing. But that's the individual behavior of galaxies where you can infer that there is this other matter out there that would account for the bizarre behavior, the seemingly bizarre behavior of the rotation rates of the galaxies. Dark energy, was the observation that the expansion of the universe is accelerating, and that implied that there was some force out there that was causing this surprising thing to be happening, and so getting a little cute, the astronomers, theorists, one in particular in Chicago, Michael Turner, came up with, we have dark matter, we'll call this dark energy, and so they're definitely separate entities, but the fact that they both have dark attached to them was sort of a branding decision.
Right. They thought those two things were linked.
Linked in that they're dark. No, we don't know what they are.
So, I mean, would it be fair to say that, I don't know anything about this, so this stuff, so this is kind of like a dark matter, dark energy for dummies, I guess. But would it be fair to say that dark matter was given that name because it appears to be some kind of obstacle that we can't see, and that dark energy is absolutely a force that we cannot see? Is that accurate?
Yeah, that's right.
So there is absolutely an obstacle that we can't see, and there's absolutely an energy we can't see.
Well, you're saying absolutely, and as I said, if a theorist comes up with a different interpretation, they've been looking for dark matter in laboratory experiments for nearly 40 years now, and they haven't found it. So so you do come up, people do come up with other interpretations.
When you describe it that way, I just picture a bunch of scientists stumbling around a laboratory in the dark.
Well, I don't know about that, but you can't say absolutely, because as I said, if somebody comes up with a different interpretation and different data,
I see,
and calls into question the data that people have already collected, for instance, the observations of the supernovae in the 1990s, if they say, well, what you weren't taking into account was there was a certain kind of dust that was affecting the measurements. And if you factor out that dust, which you wouldn't have known about in the 1990s or whatever, they knew about dust, but, whatever quality it is, they say, if somebody came up with that and said, there's this other thing out there that would have been skewing your results, then you have to go back and think about it, So I can't say absolutely.
So, I mean, it seems like, so dark matter and dark energy are just theories.
Well, no, I mean, it depends what you mean by just theories. I mean, they're based on evidence. They're based on observational evidence. So there are theoretical interpretations of observational evidence.
Okay, I see.
Yeah. In the same way that, that we infer the presence of gravity because when we let go of something, it falls,
Mm-hmm. So it could be...
So it's based on observational evidence, but, we don't see it.
So then it sounds like it's the kind of thing where we have to give some kind of explanation to the observations we're making, and dark matter and dark energy, everything that we have ascribed to those ideas seems to line up with the rest of our knowledge of the universe. And so it's like our best guess.
Yeah. Yeah, that's fair.
But it's all subject to change.
As everything in science is. That's why a while ago when you said prove, I said, I don't know about that. Because the whole idea of falsifiability that that if you come up with the observation that negates your interpretation, then you've disproven. So the in philosophy you would say you can disprove a theory, but you can't prove it because you can always you might always come up with an exception.
So is the idea that if this matter and this energy is there, but we can't perceive it, is the idea that it maybe exists in a higher plane or a different dimension or something?
I don't know that I can speak to that with dark matter, but with dark energy, that's one of the interpretations is that if there are other universes, parallel universes, which isn't as far-fetched as you might think.
Right. I actually don't think it's far-fetched.
Right. Okay. That the what we call dark energy might just be a gravitational interaction with another universe.
Right. I mean, that's what it would seem like based on everything you're saying. That seems to make total sense.
Yeah. I mean, it's theorists are looking into it. I mean, the problem with that though is how do you verify it? How do you validate it? How do you measure it? Since you can't see this other universe. But
man, that's so frustrating. That's not the answer I was looking for, Panek.
Well, sorry.
We're going to take a break to talk about the people who made this episode possible in the first place. I'm talking about Casper, the sleep brand who's continually revolutionizing its products to create an exceptionally comfortable sleep experience one night at a time. Casper's mattresses are designed by humans for humans. The original Casper mattress combines multiple supportive memory foams for a quality sleep surface with just the right sink and just the right bounce. Casper's breathable design helps you sleep cool and regulate your body temperature through the night. They're not just a mattress company. Casper offers a wide array of products to ensure an overall better sleep experience. Casper's mattresses are made in the USA, and buying the Casper is super easy. Order online, it's delivered to your door in a compact box, free shipping and free returns to the US and Canada. And considering we spend 1/3 of our lives on a mattress, it's so important to actually sleep on the thing before you commit to it. That's why Casper gives you 100 nights to try it out. Get $50 towards select mattresses by visiting casper.com/spellbound using the promo code spellbound at checkout. Terms and conditions apply. That's $50 towards select mattresses by visiting casper.com/spellbound using the promo code spellbound. All right, before we left off, I think we were talking about theories about other dimensions and things like that. And it's funny because as soon as you start talking about dimensions, I feel like a lot of people check out. But you're right, it's not far-fetched. It's honestly it's the best descriptor of what we've observed. Like the fact that there's so, not only the fact that we only have access to a small fraction of our mental power, but also we know so little about the universe. And the numbers of those two numbers, the limit of our mental capacity and the limit of our knowledge of the universe, are very similar numbers, Yeah. So it's interesting to think about the idea of dimensions because it explains a lot, and it also, what's frustrating about it is it suggests that we might not ever get to the bottom of it.
Right. Yeah. I mean, that's certainly possible. I mean, this in the history of science, I mean, the observation-based science of this sort is only about 400 years old. So this is really, this is really early days. The scale of the universe, it's stumbling around in the dark. We don't, we're just starting to put things together, even though you can look at what's happened since the dawn of the scientific revolution in the 1600s. You can look at it and say, wow, look how far we've come, but we have no idea how far we still have to go.
Right. I heard, I'm going to butcher this statistic, but I heard that we know about as much about the universe as we knew about surgery in the 1600s or something like that.
Yeah.
Which is kind of terrifying.
Well,
at least there's nobody getting, at least with these theories and stuff, you're not actually having to cut a human apart to get to the bottom of some of the answers yet.
Well, I was in the hospital about 20 years ago or so, and I was on the phone with a doctor friend. And I said, I mean, they're like guessing at what's wrong with me.
Right.
And I said, I mean, come on.
At least now medicine. They have Google.
I don't understand. And she said, look, she said, you don't understand. Medicine as we think of it is only 100 years old. I was like, oh, I see. That's why there's so much guesswork involved.
Man, well, now I don't even know where to take the conversation. Because we just covered so much ground, and then it's like, well, and there's no answers at the end of the day. The best we can do is what do you make of this stuff?
Well, let me tell you. There's something in astronomy called the anthropic principle.
I've heard of this, but remind me what it is.
Yeah, sure, of course. So the idea is that we live in this universe. This is going back to the parallel universe idea, okay. The multiverse idea. That we live in a universe that is very delicately balanced. We've been talking about dark matter and dark energy and regular matter, the kind that we always think of. And you put those together and we have a universe that is in perfect balance. By perfect balance, I mean it hasn't collapsed, which is, if anything, we're a little bit skewed in the, if any of those numbers were just a little bit off, the universe wouldn't exist.
Right. If the sun was a little bit closer to Earth, if there, right. I mean, that's a smaller level of what you're talking about, but I think I get it.
Exactly. So the anthropic principle is that we are studying this universe because we're here, because this is the universe that allows us to exist, to study it. And that we just happen to live in one of these many universes that is suitable for life to develop. And because, the idea being that if the universe comes out of a quantum pop, which is kind of the prevailing idea now.
And what's a quantum pop? Not to derail you.
Yeah, no. That's according to quantum theory. There is no such thing as nothing, as empty space. That there's always a bit of energy attached to it, and that can create this kind of, I mean, I'm calling it a pop, but it's like where something comes into existence, and if it comes into existence, it can grow into a universe. But if that's the case, according to quantum theory, if that's how the universe was made, then you would expect that simultaneously a number of other universes would have been created at the same time. And in fact, they've come up with a number for it. I have no idea where the number comes from, but it would be 10 to the 500 universes. Now, keep in mind that the number of atoms in our universe is 10 to the 80. So we're talking 10 to the 500 is way
well, yeah, this is the idea of quantum theory saying all particles manifest all possibilities in all dimensions.
Yeah, right, yeah. So if there are these 10 to the 500 other universes out there, then it starts to make sense. You go, well, one of them has the right balance has the right balance of matter and energy and gravity to sustain itself, and that's the one that we live in. And we live in the we live in the one that allows us to do that, and the other ones would have different laws of physics and would not allow us to do that. Would not allow us to exist. So this idea, I'm bringing this up because we were talking about what do you know and what can you believe. this idea has been around. I don't know how long it's been around, but it was, in my experience, I heard it entering the conversation a little less than 20 years ago. And you would hear it at astronomy or cosmology conferences. And people hated the idea. And they call the anthropic principle the A word. They wouldn't even say it.
It's aggravating.
Right. And I would sit in the back, without any science degree, I would sit there and say, saying to myself, well, we didn't know that the Earth was a planet. So then, and then we didn't know that the stars were other suns. And then we found all that out. And then we thought, okay, our galaxy is the universe. And we go, oh, wait, no, there are other galaxies out there. And now we have whatever it is, 125 billion galaxies. And so, the horizon keeps receding. And I would sit in the back and say, I don't see why we can't have other universes. I mean, I understand that they are problematic scientifically in that you can't observe them and how can you falsify their existence and so on and so forth. But I thought, but I kind of, it makes sense. Then, within 4 or 5 years, I saw this real turnaround where people were going they started to come around to it and say, it actually does make sense. And if this quantum idea that I was talking about, if that's true, and we have no reason not to think it's true, then there would be these other universes. And so it was just, for me, just sociologically, it was fascinating to see the field change in this fundamental way, to go from scoffing at this idea to accepting it as a likelihood.
Yeah, well, I mean, it makes sense that idea would be rejected at first. When it came about, because that was what, like the 70s or 80s.
Well, as I say, I mean, I don't know when the idea dates from, but I first heard of it I first started hearing about it at conferences in the early 2000s.
Oh, okay.
But it was probably around before then. I'm sure it was.
Yeah. Well, I mean, here in America, I don't know where this conference was, but in America and in Europe too, in most places in Europe anyway, whether you're religious or not, a lot of people still operate under Judeo-Christian philosophy, or whatever you call it. The idea that we're all the center of the universe is kind of Old Testament ideas, and I feel like there's been a lot of scientific breakthrough that has kind of been counterintuitive to some of those ideas that people have been living by for a long time. And so some of these ideas can sound threatening to people's worldview, especially when your whole identity is wrapped up in it.
Yeah, I suppose so. But here's another way of thinking about it. You just said, we're at the center of the universe. That idea, and you sometimes hear people say, well, the Copernican system, the idea that the Earth is orbiting the sun, that things aren't orbiting the Earth, was this blow to our ego or this demotion. And that's not the case, actually. It's the opposite. That the common feeling, you're talking about the Judeo-Christian belief system, was that we down here are different from what's up there, and that's why what's up there is perfect, and that's where God exists. And then in the Christian interpretation, that's where angels exist. So there was this idea that was the good place, and this was the garbage place, because this is where everything fell. The things up there go in circles around us, but down here, so they're perfect. Whereas down here, we know that this isn't perfect. So actually, when the idea came about that the Earth was orbiting the sun, it was threatening to the church, for instance, for many other reasons, but it wasn't because it was a demotion. In fact, Galileo, in one of his early works, said that the idea that we are orbiting the sun is actually an elevation, because it makes us equal to the heavens. So, I mean, that's a tangent, and
it's a good tangent. Let's stay on it. I like this.
And anyway, that's just in response to your musings about the Judeo-Christian system.
Yeah, so you're saying that the opposite is true, that this isn't a threat to people who subscribe to that belief system?
Well, it might be a threat in other ways. If you say that the heavens aren't perfect, I mean, if you imagine that God is up there, right, and then it turns out that you can actually know what's up there. When what is up there is mysterious, you can say, well, that's where God is. And when you take away that mystery, then you take away a little bit of the rationale for God existing. With every mystery you take away, you might be chipping away at that. That's not to say that I ascribe to that belief system, but it's where all tension between science and religion has come about.
Right, because religion kind of maybe prefers the mystery of some of it, and science is not satisfied with the mystery of it.
Right. But again, I think there is again a common misinterpretation that that science is a natural threat to religion. What science is trying to do is say, how much can we explain without invoking a supernatural cause? And by supernatural, I mean supernatural, beyond nature, beyond the natural. So that would include God. Okay?
Yeah. What can we explain with our own mental capacity that God may or may not have given us?
Right. Exactly. So it's not we're trying to disprove God. We're trying to prove what we can without invoking a supernatural cause.
Yeah, totally. Yeah, I also revoke the idea that science and faith of any kind are incompatible. I think that if you are just trying to not think about the world you live in and you don't want to know, if you can be a little apathetic with some of this stuff if you're not careful, but the idea that, even if you do believe in a creator God and that that's what made us, you have to believe that he gave us our brain, or it gave us our brain for a reason, and that, we're required to use it just like we're required to use any other part of our body for good. And learning is good. It makes us all better. It gives us answers. And I don't think anybody would deny that the progress that humans have made in other areas have been bad, like with technology, and we're figuring out a lot of our pollution problems, and these are all universal positives in my mind.
Mm-hmm. Yeah, definitely. I mean, I agree.
So what do you make of dark matter and dark energy from what you know? I mean, you're coming at this whole thing from a very unique perspective because you are clearly a person who has a brain for information, and you can soak up information and triangulate it with other universal truths that you've observed, and make opinion. Your opinions are interesting. I guess what I'm saying is, what do you make of the universe? Where do you think we're heading towards? I
don't know if this is the kind of answer you're looking for, but I get the feeling that you're asking more or less philosophically. What attracts me to these subjects, you mentioned at the beginning that I had these other books. That the first book I wrote about science, or a science-related thing, was a history of the telescope. And what attracted me to that, I have a background in journalism and I have a background in fiction. I have degrees in each of those. So this was off my usual beaten path.
Yeah.
But I was asked by an editor to look into it, and I did. And I, at first I rejected the idea, and she said, no, just think about it. Think of it as an essay. And I thought, oh, well, I've written essays, so let me look at this. And I was really attracted to the history and philosophy of science, not so much the technical nitty gritty. And I thought, okay, well, I can write about that. And through writing about the telescope, I came across this idea of dark matter and dark energy, and that just kind of blew me away. But that didn't belong in that book, because it's like I got to that point in the book, and I went, "Whoa, wait a minute! There's this whole other subject out there," and that's when I started researching. That was like the first inkling of this book that we've been discussing, the 4% universe. But between the telescope book and this book, I did a book on Einstein and Freud, because I liked the idea when I was researching the telescope book that there are these areas that are outside of our vision. That what we see a very small part of the electromagnetic spectrum. And if we had eyes that could see X-rays or gamma rays or ultraviolet light or infrared, etc., we would see the universe in a completely different way. So I like the idea of there being like this invisible side of the universe, which is why I called it the invisible century. And I wrote about how these ideas came about on the physics side, but also how they were influencing ideas like about the unconscious that Freud was exploring around the same time. So I went from thinking about the universe one way, which is just as this visible thing that you look at through the telescope. And then I found out that you could see all these other things outside of the visible part of the electromagnetic spectrum, and that they all had their own identities. So, that was the next book. And then in writing about that, dark energy became, while I was working on that, dark energy became a real going concern, and people, were accepting it. And then I thought, so now you've got dark matter and dark energy, and so most of the universe is not visible to the eye, but is not visible in any part of the electromagnetic spectrum. So now we're at a whole other level of ignorance and mystery. And so so when you ask me about how I see the universe, I've experienced it in this kind of widening way of having my assumptions overturned. And I love the idea that we go through life or go through civilization with these unthinking assumptions. To get back to dark matter for a second, one of the astronomers who discovered the evidence that would lead people to theorize about dark matter, her name was Vera Rubin, and she died just about a little over a year ago. But I got to know her fairly well through my research, and she was great. But she had this great quote, which she didn't give to me, but I read it several times. That in the early days, when people were talking about dark matter and whether or not this was a concept to be taken seriously, she said, "Nobody ever told us that all matter radiated. We just assumed that it did." Meaning, nobody ever told us that everything we could see in the universe was going to be, or everything in the universe was going to be accessible through the electromagnetic spectrum. We just assumed that it would, So it was a new idea, and people had to wrap their heads around it. So I like that idea that our unthinking assumptions can be challenged in this really, kind of fundamental way where you go, oh, I get it. That big aha moment.
Yeah. I mean, it sounds like you're kind of saying that you reach a moment where you learn so much that you realize how little any of us actually know.
Yeah. Well, people often think, non-scientists I'm talking about, often think that the purpose of science is to find answers. And that's true. But, you talk to a scientist, and one of the other purposes of science is to find questions, to find the new questions. So you get an answer, and but then it opens up another door. And in fact, one of the, here's a really great example, I think, that the Large Hadron Collider found the Higgs boson, right? That was a big deal, but everybody knew that that's what the Large Hadron Collider was going to find. That's what it was built to find. So while people are excited about that, they're also disappointed that it hasn't found other mysteries. So, they asked a question of the universe, does the Higgs boson exist? If it does, we're going to find it with this machine. It does exist. We found it. Now, where's the next question? They expected questions to fall out. They expected to get an answer, but they wanted questions as well. And they're disappointed that they didn't get them, or they haven't been getting them.
Yeah, questions can be more powerful than answers sometimes. Sure.
It's the next stage of discovery.
Well, I mean, we just covered so much there. I don't even know what else we would say. Is there anything that we didn't talk about that you wish we had talked about?
Yeah, just briefly, I'll say that that progression that I was talking about a few minutes ago, that in my own researched. I went from the visible to the invisible to the unseeable. The book I'm working on now, I'm finishing it in the next month or so, is about gravity and the fact that nobody knows what gravity is, and that idea just blows me away. That nobody knows what gravity is, but we all take it for granted.
Yeah, that's a really interesting thought. Yeah, it's such a strange. I mean, if you're a flat earther, you think we're just accelerating through space on a flat plane, and that's what gravity is. But that's not a good enough answer, maybe. It's not very helpful. Not to bash the flat earthers. I don't want to start a protest here, but yeah, I can't wait to read that. When is that book out, and what is it going to be called? Do you know?
It's called The Trouble with Gravity, Solving the Mystery Beneath Our Feet, and it's coming out in January.
I cannot wait to read that. That's exciting. Well, I am so glad that you made time for this call. It was awesome talking to you and hearing your thoughts on all this stuff. Your brain is very, I love the way you think about things and the way you approach questions.
Well, thank you. That was a real pleasure to be here.
Look forward to talking to you soon.
Okay, thanks.
Thanks, Richard. Bye-bye. I want to hear your thoughts on this conversation. If you're listening on YouTube, join the thousands of other listeners who are sharing their thoughts in the comments section. Or if you have something longer you want to say, you can shoot me an email, hello@spellboundshow.com. That goes directly to me. Be sure to hit that subscribe button so you never miss an episode. That way your phone will always stay up to date. Special thanks to Richard Panek for joining us. Be sure to check out his book, The 4% Universe, and his numerous other books as well. They're all worth reading, especially the one that he wrote with Temple Grandin, who was on the show a few weeks ago. That one might be interesting to you guys, The Autistic Brain. She actually referenced that book in that episode, and Richard co-wrote it with her, so that's kind of cool. I'm Julian Smith. This has been Spellbound. I hope you enjoyed it as much as I did, and I look forward to speaking with you guys again next Monday. Have a great week.